there's something down there. Not on the surface, not in the rocks that the rovers have been drilling and analyzing and photographing for 2 decades. Beneath the surface, under the ancient volcanic plains and the sedimentary layers and the permafrost and the regolith. Something that the radar instruments designed to pierce the Martian ground with radio waves and listen for what bounces back, are detecting in patterns that the scientists who built them are struggling to explain. I want to be precise about this from the beginning. Radar sounding of planetary surfaces is not exotic or speculative. It's a well-established technique with a rigorous mathematical foundation. The same basic physics that underlies ground-penetrating radar used in terrestrial archaeology and civil engineering underlies the instruments orbiting Mars and rolling across its surface. You send a radio wave into the ground. It propagates downward until it encounters a boundary, a change in the dielectric properties of the material, which happens wherever there's a change in composition, density, or critically, the presence of a different phase of matter. Ice versus rock. Rock versus liquid. Air versus dense substrate. At every such boundary, some of the radar energy is reflected back upward, and the timing and amplitude of that reflection encodes information about the depth and nature of the boundary. The physics is clear. The instrumentation is validated. The teams operating these instruments are among the most experienced radar scientists on Earth. And what they're finding in the data from 3 separate radar instruments, 2 in orbit and 1 rolling across the Martian surface, is a picture of the Martian subsurface that doesn't match what the geological models of Mars predicted. There's something down there, multiple somethings at multiple depths in multiple locations. Some of them are consistent with known materials and known configurations. Some of them are not. And the ones that aren't the anomalies, the unexpected reflectors, the features that require explanations that go beyond the simple models, are the subject of an increasingly urgent and increasingly technical scientific debate. Let me take you through what the radar is seeing, what it means, and why the answer, whatever it turns out to be, is one of the most important things we could possibly find on another planet. Let me start with the instruments themselves. Because understanding what they can and can't detect is essential for interpreting what they've found. The first and most powerful radar sounder currently operating at Mars is MARSIS, the Mars Advanced Radar for subsurface and ionosphere, sounding aboard the European Space Agency's Mars Express orbiter. MARSIS has been operating since 2005, making it the longest-running subsurface radar instrument in planetary science. It operates at low frequencies between 1.8 and 5 megahertz, which allows it to penetrate deep into the Martian crust. The penetration depth, depending on the material, can reach several kilometers. The trade-off is resolution. MARSIS can detect large-scale subsurface features, but can't resolve details smaller than a few hundred meters horizontally and tens of meters vertically. The second orbital radar is SHARAD, the Shallow Radar Sounder, aboard NASA's Mars Reconnaissance Orbiter, operating since 2006. SHARAD operates at higher frequencies, around 20 megahertz, which provides better vertical resolution but less penetration depth. Where MARSIS sees deep and coarsely, SHARAD sees shallower and more precisely. The 2 instruments are complementary. They probe different depth ranges and provide different types of information about the same Martian underground. The third instrument is the most recent and in some ways the most remarkable RIMFAX, the radar imager for Mars's subsurface experiment, riding aboard the Perseverance rover on Mars's surface since February 2021. Unlike the orbital sounders, which look down from space through a column of atmosphere and then into the ground, RIMFAX is physically on the surface, rolling across it, firing radar pulses straight down with every rotation of the rover's wheels. It operates at frequencies between 150 and 1,200 megahertz, much higher than the orbital sounders, which gives it centimeter-scale vertical resolution at depths of up to about 10 meters. RIMFAX is essentially creating a continuous cross-section of the shallow subsurface as Perseverance drives, producing what scientists call a radargram, an image of the underground structure stretched out beneath the rover's path. 3 instruments, 3 different depth ranges, 3 different spatial resolutions, all of them from their different vantage points looking at the same Martian underground, and all of them finding things that weren't expected. Let me start with the discovery that generated the most controversy, the one that has been argued about in the planetary science community for nearly a decade, and that new data keeps both supporting and complicating. In 2018, a team led by Roberto Orosei of the Italian National Institute of Astrophysics published a paper in Science reporting a specific anomaly in Mars's data from the south polar region of Mars. The south polar layer deposits a stack of water, ice, and dust layers covering an area roughly 1,000 kilometers across, built up over millions of years of Martian climate cycles, had been studied by Marsus since 2007. The radar data from this region was in most ways exactly what the models predicted. Ice layers of varying composition, the basal unit of the polar cap, the underlying bedrock, but in one specific region beneath the south polar layer deposits at a depth of about 1.5 kilometers, Marsus detected an anomaly, a bright reflector, not just bright in the sense of reflecting more radar energy than the surrounding ice, extremely bright. The reflectivity of this feature exceeded the reflectivity of the surface ice above it. In the physics of radar sounding, for a subsurface reflector to be brighter than the surface, its dielectric contrast must be higher than the contrast between ice and vacuum. The material at this reflector must have a dielectric permittivity, a measure of how strongly it responds to electromagnetic fields dramatically higher than ice. The dielectric permittivity of water ice is about 3. Rock is 4 to 9. Dry regolith is similar. Brine, highly saline, liquid water is 15 to 20. Liquid water is about 80. The only naturally occurring material on Mars with a dielectric permittivity high enough to produce a reflector brighter than the overlying ice surface is liquid water, or something with similar electromagnetic properties. The Marsus anomaly, in the interpretation of Orosei and colleagues, was consistent with a pool of liquid water, perhaps 20 kilometers across and at least a few tens of centimeters thick, buried 1.5 kilometers under the South Pole. Liquid water on Mars, not ancient, dried up evidence of water, not ice, liquid water existing right now under the South Pole. The reaction from the scientific community was immediate and divided. On one side, researchers who accepted the liquid water interpretation. The radar physics is clear. Something with high dielectric permittivity is down there. Liquid water fits the data. The depth and temperature are challenging. At 1.5 kilometers under the ice cap, the temperature should be around minus 68 degrees Celsius, far below the freezing point of pure water, but perchlorate salts, which are known to be abundant in the Martian soil from measurements by the Phoenix lander and the Curiosity rover, dramatically lower the freezing point of water. Calcium perchlorate solution can remain liquid at temperatures as low as minus 74 degrees Celsius. The temperature is at the edge of what hypersaline water could sustain, but not impossible. On the other side, researchers who questioned the liquid water interpretation, the most persistent objection involves the temperature. Even with perchlorate antifreeze, maintaining liquid water at 1.5 kilometers depth under the south polar ice cap requires a heat source geothermal heat flowing up from the interior. The estimated geothermal heat flux at the Martian South Pole, based on models of the planet's cooling history, is about 25 to 30 milliwatts per square meter. The heat flux required to to maintain liquid water at 1.5 kilometers depth under the ice cap is substantially higher, perhaps 2 to 3 times higher than these estimates. Where is the extra heat coming from? The answer might be local volcanic hotspots. Mars is not completely volcanically dead. We've established this in earlier conversations. Specific regions, particularly in the Tharsis volcanic province, show evidence of recent geological activity. If there are localized magmatic intrusions, bodies of hot rock injected into the crust relatively recently, they could provide the local heat flux needed to maintain liquid water under the South Polar Cap, even with a globally low geothermal gradient. The alternative interpretation, the one that doesn't require liquid water, involves the specific electromagnetic properties of certain types of clay minerals or volcanic ash deposits. Some materials, particularly smectite clays, have dielectric permittivities higher than dry rock, high enough perhaps to produce a brighter than surface reflection. If the base of the South Polar ice cap is resting on a layer of volcanic ash or specific clay minerals with elevated dielectric properties, the Marsus reflection might be entirely abiotic and dry. But here's the problem with the clay and ash interpretation. Subsequent analyses using updated processing algorithms and additional Marsus data accumulated since the original 2018 paper have found not one bright reflector, but multiple bright reflectors under the South Polar Cap in different locations at slightly different depths. Not a single anomaly, a pattern of anomalies. Multiple bright reflectors covering a total area comparable to the size of a large lake system. A single anomaly might be explained by a localized deposit of unusual material. Multiple anomalies in a pattern consistent with subice water bodies are harder to explain with dry mineral hypotheses. Now let me tell you about what Sharad has been finding. Because while Marsus has been generating the most debate, Sharad's contributions to the subsurface picture of Mars are in some ways even more scientifically significant and in several cases even harder to explain. Sharad has been mapping the shallow subsurface, the top kilometer or so, of large areas of Mars since 2006. Its higher frequency and better vertical resolution reveal fine structure in the layered deposits, buried impact craters, volcanic flows, and glacial ice deposits that Marsus is too coarse to resolve. The global data set it has accumulated is extraordinary, covering essentially the entire planet multiple times. The most unexpected finding from Sharad isn't at the poles, it's in the mid-latitudes. Specifically, in a region called Medusae Fossae Formation, a vast deposit of fine-grained material covering several million square kilometers near the Martian equator, extending over the border of the Tharsis volcanic province. The Medusae Fossae Formation has been a puzzle since it was first identified. Its composition is uncertain, its origin is uncertain, its radar transparent radio waves pass through it with unusually low loss, which is itself diagnostic. High radar transparency in planetary materials indicates either very pure, fine-grained ice or extremely dry, porous silicic rock with very low electrical conductivity. Sharad has probed the Medusae Fossae Formation in detail, and what it's found is that the formation is thicker, more laterally extensive, and more structurally complex than surface imaging suggested. More importantly, in certain regions within the formation, Sharad is detecting internal reflectors boundaries within the formation that reflect radar energy, whose geometry is inconsistent with simple volcanic or aeolian deposition. Some of these internal reflectors have the geometry of buried ice-cemented deposits, layers that were deposited in a specific orientation and then partially cemented by ice, infiltrating from above or below. If this interpretation is correct, the Medusae Fossae Formation contains a substantial buried ice inventory at equatorial latitudes, a finding with major implications for the history of Mars's water and for future human missions that might need water resources far from the poles. But others of the internal reflectors don't fit this picture. Their geometry, their orientation, their lateral extent, their specific reflection coefficients is inconsistent with ice-cemented sediment and inconsistent with simple volcanic layering. The Sherrod team is still working through what these anomalous internal reflectors represent. The interpretations in the literature range from buried lava tube networks, hollow subsurface channels of the kind we discussed in the Artemis conversation, to stratified brine aquifers, to deposits of specific minerals with unusual electromagnetic properties. The honest answer from the scientists working with this data is, we don't know. The radar is seeing something. What it is requires ground truth, direct sampling, direct measurement, that no instrument currently at Mars can provide. Now let me take you to what I think is the most scientifically precise and the most immediately consequential of the three radar stories. What RIMFAX is finding as Perseverance drives across Jezero Crater. The Jezero Crater story we've discussed before. It's the ancient lake bed where Perseverance is searching for biosignatures, drilling cores for eventual return to Earth. We know Jezero was a lake. We know water flowed into it from river channels. We know sediment accumulated on its floor over millions of years. What we didn't know, what no instrument before RIMFAX could reveal, is what the layered structure of that sediment looks like beneath the surface, and whether it's consistent with the simple geological story of a lake that filled accumulated sediment and dried up. The answer from RIMFAX is no. The subsurface structure of Jezero Crater is not consistent with a simple lake fill and dry out history. RIMFAX data published in Science in 2024 revealed that the shallow subsurface of the Jezero Crater floor has a specific geometry that the Perseverance science team describes as unexpected and complex. The radar reveals horizontal layers consistent with sedimentary deposition, but these layers are cross-cut by structures that have the geometry of fractures, intrusions, or channels, features that formed after the sedimentary layers were in place and that disrupted and cut through them. The most significant of these post-sedimentary features are vertical or steeply dipping reflectors that cross-cut the horizontal sedimentary layering. In terrestrial geology, this geometry, vertical structures cutting through horizontal layers, is characteristic of either tectonic fractures, hydrothermal vents, or fluid migration pathways. It's the geometry you'd expect if fluids, water, or volatile-rich hydrothermal fluids had moved upward through the sedimentary pile after it was deposited, carving channels through it. This is extraordinary. It means that Jezero Crater didn't just have a lake on its surface 3.5 billion years ago. It had subsurface fluid activity, hydrothermal or hydrous, after the lake dried up. The water didn't just leave, it went underground. And it continued to move, to interact with the rock, to potentially support chemical reactions and possibly biology in the subsurface long after the surface became the dry, frozen desert we see today. The connection to the astrobiology question is direct and unavoidable, because on Earth, when we find the geometric signature of subsurface fluid pathways in ancient sedimentary sequences, the vertical fractures cutting through horizontal beds, we consistently find evidence of microbial activity associated with those pathways. The fractures are channels along which chemotrophic bacteria migrate, metabolize, and leave biosignatures, organic compounds, isotopic fractionations, mineral textures that we can detect in the ancient rock record billions of years later, if Jezero's subsurface fracture network was inhabited by chemotrophic bacteria 3 billion years ago, bacteria that use the chemical energy of the hydrothermal fluids moving through the fractures, those bacteria might have left biosignatures in the rock that cores from the fracture zones could contain. And Perseverance has been collecting cores specifically from locations that RIMFAX has identified as being near or above these subsurface structural features. The cores are cached. They're waiting for the Mars sample return mission. When they reach Earth, and when the laboratories of Earth bring the full power of modern analytical chemistry to bear on them, the subsurface architecture revealed by RIMFAX will tell us exactly where to look. But let me now go beyond the specific findings and address the broader picture that the three radar instruments are collectively painting. Because individually, each discovery is significant. Together, they're telling a story about Mars that is fundamentally different from the Mars that was understood before these instruments began operating. The standard model of Mars, the model that prevailed from the Viking era through the early Mars Reconnaissance Orbiter era, was of a planet that had been wet in its earliest history, dried out rapidly as its atmosphere thinned and its magnetic field weakened, and has been essentially geologically and hydrologically dead for the past 3 billion years. A frozen, desiccated, internally cold world whose water is entirely locked up as surface and near-surface ice, primarily at the poles. The radar picture that's emerging is of a Mars that is internally more active, hydrologically more complex, and structurally more varied than this standard model assumed. A Mars with possible liquid water at depth under the poles, sustained by geothermal heat that the models may have underestimated. A Mars with extensive buried ice at equatorial latitudes, far from the poles where surface stability arguments predict ice shouldn't be. A Mars whose ancient sedimentary basins preserve evidence of prolonged subsurface fluid activity that continued long after the surface dried out. And a Mars whose shallow subsurface is cut through with fracture networks and structural heterogeneities that provide the physical pathways for fluids and for life to persist in the deep subsurface long after surface conditions became lethal. There's something down there. Not necessarily life, though. That's the question that makes everything else relevant. But definitely water in forms and locations and quantities that the pre-radar models didn't predict. Definitely geological activity in the form of fluid movement and heat flow and structural complexity that challenges the cold, dead Mars paradigm. And definitely specific locations, the South Polar Bright Reflectors, the Medusae Fossae anomalous reflectors, the Jezero fracture network, that are worth investigating further and that represent our best current candidates for environments where liquid water might have persisted or might still persist long after Mars's surface became hostile to life. In part 2, I want to go deeper into the physics of what these radar systems are detecting, into what the specific reflection coefficients and dielectric properties are actually telling us about the composition of these anomalous features. Into the growing debate about the South Polar liquid water hypothesis and the specific recent data from both Mars's updated analysis and from independent geophysical modeling that is pushing the community toward or away from the liquid water interpretation. And into what the next generation of instruments, including the ice-penetrating radar planned for future Mars missions, could definitively resolve. There's something down there. The instruments have told us that. What it is, and whether it's the thing that changes everything we thought we knew about whether Mars was ever or still is alive, that's what the science is working toward. So we'd arrived at this place where 3 independent radar instruments, MARSIS, SHARAD, and RIMFAX, are collectively painting a picture of the Martian subsurface that is fundamentally more complex, more hydrologically active, and more scientifically surprising than the standard model of a cold, dead, desiccated Mars predicted. bright reflectors under the south polar ice cap consistent with liquid water. Anomalous internal structure in the equatorial Medusae Fossae formation, subsurface fracture networks in Jezero crater indicating prolonged post-lacustrine fluid activity. Now I want to go deeper into the specific physics that makes these anomalies so hard to explain away, into the most recent data published through 2025 that is sharpening the debate about what these features actually are, and into something that I think is the most scientifically consequential aspect of the entire story, the specific connection between the RIMFAX findings in Jezero and the actual biosignature samples that Perseverance has already collected and cached. Let me start with the physics. Because the radar anomaly debate ultimately comes down to specific numbers, specific dielectric permittivities, specific reflection coefficients, and understanding those numbers is what allows you to distinguish between a genuine discovery and a misinterpretation of the data. When a radar wave traveling through a medium encounters a boundary with a different dielectric permittivity, the fraction of the wave's energy that is reflected depends on the contrast between the two media. This is described by the Fresnel equations, the same equations that describe the reflection of light at an interface between two materials with different refractive indices. The power reflection coefficient, the fraction of incident power reflected back, is proportional to the square of the dielectric contrast. For the Marsus south polar anomaly, the observed reflection coefficient at the bright reflector is approximately 10 times higher than the reflection coefficient at the surface. This is the key number. And it's this number, the factor of 10 enhancement in reflectivity relative to the surface, that constrains the possible identities of the material at the reflector. Let's go through the candidate materials systematically. Dry rock, basalt, granite, sandstone has a dielectric permittivity of roughly 4 to 9. Water ice has a permittivity of about 3. The contrast between ice and dry rock produces a reflection coefficient that is smaller than the contrast between ice and vacuum at the surface, meaning a rock-ice boundary should be dimmer than the surface, not brighter. Dry rock cannot explain a reflector 10 times brighter than the surface. Volcanic ash, highly porous, fine-grained volcanic material, has a permittivity of roughly 2 to 4, depending on porosity. Ice-ash boundary, dimmer than surface, cannot explain it. Specific clay minerals, smectite clays in particular, have permittivities ranging from 5 to 15 depending on water content. The high end of this range, at high hydration, approaches the values needed to explain the Marsus anomaly. This is the strongest non-water alternative, and it's been taken seriously in the literature. But getting smectite clay with permittivity approaching 15 requires substantial water of hydration, and clay minerals at 1.5 kilometers depth under a polar ice cap at temperatures of minus 68 degrees Celsius would not be highly hydrated. The water of hydration would be frozen into the mineral structure, reducing the permittivity to values similar to dry rock. Carbon dioxide ice, which is present in the polar caps, has a permittivity of about 2.1, even lower than water ice. A CO2 ice layer beneath water ice would produce a reflector dimmer than the surface. Cannot explain it. Brine, liquid water with high salt concentration, has a permittivity ranging from roughly 20 for moderately saline solutions to near 80 for very dilute water, with the specific value depending on temperature and salt concentration. Even at the extreme temperatures under the south polar cap, hypersaline perchlorate brines maintain high dielectric permittivity, roughly 15 to 20 at minus 70 degrees Celsius. This is high enough to produce a reflector substantially brighter than the ice vacuum surface. Liquid water, even slightly saline at any temperature above its freezing point, has a permittivity approaching 80. An ice-liquid water boundary would produce a reflection coefficient dramatically higher than the ice vacuum surface. The physics constrains the options. The bright reflectors are consistent with liquid water or concentrated brine. They are inconsistent with all known dry materials at the relevant temperatures, with the possible exception of very specific, very unusual clay mineralogy that requires its own explanation. Now let me tell you about the most important development in the South Polar Radar story since the original 2018 Science paper, a series of papers published between 2022 and 2025 that have significantly complicated and enriched the picture. The 2022 complication came from a re-examination of the MARSIS data processing. A team led by Aditya Kular at NASA's Jet Propulsion Laboratory identified a potential artifact in the signal processing pipeline that could, under specific circumstances, produce spuriously bright reflectors in the radar data. The specific artifact, called the range side lobes problem, arises from the way MARSIS's onboard processor compresses and decompresses the radar pulses. Under certain conditions of surface roughness and subsurface geometry, this processing can create ghost reflections that appear brighter than they should. This was a significant concern. It raised the possibility that the bright south polar reflectors were processing artifacts rather than physical features. The planetary science community took this seriously. Multiple groups reanalyzed the data using alternative processing methods designed to suppress or eliminate the side lobe artifact. The result was mixed, but ultimately more supportive of the original interpretation than not. When the alternative processing is applied, the bright reflectors are reduced in apparent reflectivity, but they don't disappear. A significant fraction of the apparent brightness remains after side lobe correction. The feature is real. It's not entirely an artifact. But its true reflectivity may be somewhat lower than the original analysis suggested. This revision doesn't eliminate the liquid water interpretation, but it reduces the certainty. Instead of a reflection coefficient 10 times the surface, the corrected analyses give a factor of perhaps 5 to 7. Still too bright for dry materials, still consistent with brine or liquid water, but with a somewhat narrower range of possible explanations. Then, in 2023, a study using a completely independent approach, geophysical modeling of the thermal structure under the South Polar Cap, provided a specific prediction. Using updated measurements of Mars's crustal thickness from the InSight seismometer data and updated estimates of the heat-producing element abundances in the Martian interior, the study computed the expected temperature at 1.5 kilometers depth under the South Polar Cap. The result was minus 70 degrees Celsius, consistent with the earlier estimates and right at the edge of what perchlorate brines can sustain as liquid. But the study also identified a specific scenario that could raise the temperature enough: the presence of a localized magmatic intrusion, a body of cooling magma injected into the crust beneath the South Pole within the past few 100 million years. Such an intrusion would provide the additional geothermal heat needed to maintain liquid brine at 1.5 kilometers depth. And crucially, MARS's data from the South Polar region shows evidence of volcanic edifices and potential intrusive features in the subsurface geology in the broader region. The picture that's emerging is specific and testable. The South Polar bright reflectors are most likely hypersaline perchlorate brines, not pure liquid water, maintained at or just above their freezing point by a combination of the depressant effect of the salts and localized geothermal heating from a relatively recent magmatic intrusion. The brine is probably not a deep, connected aquifer. It's more likely a series of disconnected, thin pockets of extremely salty water, perhaps only centimeters to meters thick, trapped in specific geological configurations beneath the ice. Not a lake, a set of brine pockets, cold, salty, barely liquid, but liquid. Now I want to address the most important question about these hypothetical south polar brines, the one that makes everything else relevant. Could anything live there? The conditions are extreme by any standard. Temperature around -68 to -70 degrees Celsius. Salt concentrations far exceeding the salinity of Earth's ocean, perhaps 40 to 50% salt by mass, dominated by calcium and magnesium perchlorates. No sunlight buried under 1.5 kilometers of ice. No obvious energy source except the chemical energy of the water-rock interactions occurring at the base of the brine layer. On Earth, life exists in environments that are individually comparable to each of these extremes. Psychrophilic bacteria in Antarctic brine pockets survive at temperatures down to -20 degrees Celsius and remain metabolically active, if slowly. Halophilic archaea thrive in saturated salt solutions, the Dead Sea, the Don Juan Pond in Antarctica, at salt concentrations approaching those that might exist in the Martian brines. Chemolithotrophic bacteria in deep subsurface aquifers metabolize using the chemical energy of water rock reactions without any sunlight. But combining all of these extremes, simultaneously extreme cold, extreme salinity, no light, no surface chemistry, produces a set of conditions that has no known terrestrial analog. The closest is the Don Juan Pond in Antarctica's Wright Valley, a shallow pond of calcium chloride brine that remains liquid at -50 degrees Celsius with salt concentrations approaching 40% in an environment with essentially no primary productivity from sunlight. Studies of Don Juan Pond have found that it's largely abiotic. Microbial diversity is extremely low compared to other extreme environments. The chemistry is so hostile that even the hardiest known extremophiles struggle to establish populations. The Martian South Polar brines, if they exist, would be colder and saltier than Don Juan Pond. The probability of life there is not zero. No planetary scientist would make that claim, but it's low. The conditions are at or beyond the known limits of life as we understand it. The more promising targets for Martian subsurface life, if it exists, are not the polar brines. They're the deeper, warmer aquifers that might exist at greater depths where the geothermal heat flow brings the temperature above the freezing point even of pure water. And they're the shallow subsurface fracture systems like those RIMFAX has detected in Jezero environments that were active more recently that connected to the surface chemistry of the ancient lake, and that might have been habitable for much longer periods than the current polar brines. Let me now tell you about the RIMFAX story in more detail, because I think it's the most immediately relevant to the biosignature search, and the recent publications from the Perseverance science team have added significant new layers to what was already a remarkable finding. The initial RIMFAX publications in 2022 and 2023 established the basic picture, the horizontal sedimentary layers, the post-sedimentary vertical and steeply dipping structures, the evidence for fluid migration through the Jezero subsurface after the lake dried up. In 2024, a more detailed analysis was published that quantified the properties of the subsurface structures in specific locations where Perseverance had drilled core samples. The analysis revealed something specific and extraordinary. In several locations where the science team had already identified rocks of high astrobiological interest, rocks with elevated carbonate content, with clay mineral signatures, with potential organic compound associations, the RIMFAX data shows that these surface rocks are directly above the subsurface fracture network. The fractures extend downward from near the surface into the deeper sedimentary pile. The surface rocks are, in the language of the paper, hydraulically connected to the deeper subsurface through these fracture systems. What this means physically is that fluids moving upward through the fracture system from below could have reached the surface or near surface rock that Perseverance has been sampling. The carbonate minerals that make the margin unit rock so scientifically interesting, the minerals that on Earth efficiently trap and preserve organic molecules may have precipitated from fluids that came from below, from the hydrothermal system, rather than from the surface lake water above. This is significant for two reasons. First, it potentially extends the habitable window. A surface lake existed for a finite period, perhaps tens of millions of years, based on the sedimentary record. But a subsurface hydrothermal system, sustained by slow geothermal heat flow and the chemistry of water-rock reactions, could persist for hundreds of millions of years, far longer than the surface lake. Any organisms that colonized the subsurface fracture system during the lake period could have continued to inhabit it long after the lake dried up, retreating deeper as surface conditions became hostile, surviving on the chemical energy of the hydrothermal system. Second, and more immediately practical, it means the cached Perseverance core samples may contain biosignatures of both surface and subsurface origin. Not just the signature of photosynthetic or chemosynthetic organisms living in the lake water, the signature of subsurface chemolithotrophs living in the fracture system, whose products were carried upward by the ascending hydrothermal fluids and deposited in the carbonate minerals at the surface or near surface. The cores are the window. RIMFAX has shown us that the window opens not just onto the ancient lake, but onto the deeper subsurface ecosystem, if one existed. The analyses that will be performed on those cores when they reach Earth laboratories are not just testing whether life existed in the lake, they're testing whether life existed in the Martian subsurface and left its traces in the rock through which its chemical environment flowed. Now let me take you to something that I find genuinely surprising about the radar story, a finding from SHARAD that received relatively little public attention, but that the planetary science community regards as one of the more important Mars discoveries of the past several years. In 2022, an analysis of SHARAD data from the Hellas Basin, the largest confirmed impact crater in the solar system, a vast depression in the southern hemisphere of Mars that descends nearly 8 kilometers below the mean Martian surface level, revealed a specific subsurface structure in the basin's eastern rim. The Hellas Basin is scientifically interesting for several reasons. Its extreme depth creates the highest atmospheric pressure on Mars's surface, still only about 1.2% of Earth's sea level pressure, but substantially higher than the global average. This elevated pressure extends the range of conditions under which liquid water could exist at the surface, at the floor of Hellas. The temperature and pressure conditions are closer to those where liquid water is stable than anywhere else on Mars's current surface. But the SHARAD finding isn't about the basin floor. It's about a specific region of the eastern rim, a terrain called Hellas Planetia's Eastern Escarpment, where SHARAD detected a series of subsurface reflectors at depths of 100 to 800 meters that have a geometry entirely inconsistent with simple volcanic or impact-deposited stratigraphy. The reflectors dip systematically, they're tilted, consistently inclined in the same direction over a horizontal extent of hundreds of kilometers. This systematic dip is the geometric signature of a sedimentary sequence deposited in a specific depositional environment, not random volcanic layering, not random impact ejecta, but organized, directed deposition. The geometry is most consistent with either a large ancient lake deposit or a glacial deposit material laid down by water, or ice flowing in a specific direction and settling in a specific configuration. More remarkably, some of the reflectors at the deeper end of the sequence, at depths approaching 800 meters, show the same kind of anomalously high reflectivity that the south polar reflectors show. Not as extreme, not the factor of 5 to 10 enhancement seen at the South Pole, but higher than expected for simple rock ice or rock sediment boundaries. The interpretation that the Sherrod team is most seriously considering is that the deep Hellas Eastern Escarpment reflectors represent a buried sequence of ancient lake sediments, sediments deposited in a large body of water that occupied the eastern Hellas basin perhaps 3 to 4 billion years ago, with specific layers that were subsequently infiltrated by water or brine, leaving their elevated dielectric signature preserved in the radar data. Hellas Basin, as an ancient lake system, possibly the largest lake system in Mars's history, given the basin size, with preserved subsurface sedimentary record reaching nearly 1 kilometer into the rock. This is a target for future radar-equipped landers and rovers that is arguably as scientifically significant as Jezero Crater. And it's one that, before Sherrod, was not on the priority list for astrobiological investigation. Let me now address the most fundamental question that all of this radar data raises, the question of what it would mean for our understanding of Mars, and for the question of whether Mars ever harbored life, if the liquid water interpretation of the south polar reflectors is confirmed. The key issue is timing. When was the liquid water, if that's what it is, emplaced? How long has it been there? Has it been continuous, or has it frozen and thawed repeatedly over geological time? These questions matter for the life question because microbial life, once established in a liquid water environment, can persist through extraordinary extremes, including partial freezing, if the liquid water environment was sufficiently long-lasting and stable initially for life to establish itself. The South Polar ice cap itself has been accumulating over the past few million years. The specific layered deposits that Mars has probed are relatively young by geological standards. The bright reflectors at the base of the ice cap might be young as well, perhaps only a few million years old. If so, they were emplaced when Mars's surface was essentially, as it is today, cold, dry, irradiated, hostile. Life originating in such an environment from scratch is essentially impossible. The South Polar brines, if they're young, are almost certainly abiotic. But there's an alternative possibility. The South Polar bright reflectors might not be young brines emplaced recently. They might be ancient water pockets, remnants of a much larger subsurface water system that has been slowly freezing from the top down over billions of years, retreating to greater depths, becoming more saline as the less salty fractions froze out, leaving behind the most concentrated, most freeze-resistant brine pockets as the frozen interface descended. If this is correct, if the South Polar brines are the last remnants of an ancient, deep aquifer system that was liquid throughout Mars's early habitable history, then they have been liquid continuously or near continuously for billions of years, long enough for life to have established itself when conditions were better during the warm, wet early Mars period, and then adapted to the progressively more extreme conditions as the water retreated and concentrated. This is the scenario that makes the South Polar brines genuinely interesting for astrobiology rather than merely interesting for hydrology. Not as an environment where life currently thrives, as an environment where life might have retreated, where the last most heat and salt-tolerant descendants of ancient Martian biology might be metabolizing extremely slowly at the very edge of what chemistry can sustain. The radar can tell us that something with high dielectric permittivity is there. It cannot tell us whether that something is ancient or young, continuously liquid or recently thawed, connected to a deeper system or isolated. Answering these questions requires ground truth that no current instrument can provide, either a deep drilling mission to the South Polar region or, more practically, geophysical modeling constrained by seismic data from the InSight mission combined with updated thermal evolution models. The InSight seismometer, which operated from 2018 to 2022, before its solar panels were covered by dust detected hundreds of Marsquakes and provided the first direct measurements of Mars's internal structure, the crust thickness, the core size, the seismic velocity structure. All of these constrain the thermal evolution models that predict how quickly the interior has cooled and how much geothermal heat is available to maintain liquid water at depth. The InSight data is still being fully analyzed, and the results continue to feed into the South Polar water debate. Let me tell you about something that I find most remarkable about the collective picture that the radar instruments are building something that goes beyond any individual discovery. The radar data is showing us that Mars is not a simple planet, not a simple geological history, not a simple hydrological history, not a simple thermal evolution. It's a planet with regional heterogeneity, with specific locations where conditions are significantly different from the global average, where heat flow is locally elevated, where water has been concentrated and preserved, where ancient subsurface environments have been sealed off from the deteriorating surface conditions and might have maintained habitability far longer than the global models suggest. This regional heterogeneity is important for the life question. Life doesn't need the whole planet to be habitable. Life needs specific environments, specific niches, where the right combination of liquid water, chemical energy, and stable physical conditions exists. On Earth, life occupies the full range of accessible environments, but life's origin, the specific event or process that produced the first living system, required only one favorable environment somewhere at some time. The radar data is finding multiple such environments on Mars, environments that were habitable or might still be habitable, or preserve a record of past habitability in specific localized regions, while the rest of the planet was or is hostile. The South Polar brines, the Jezero fracture system, the Hellas Basin deep sediments, the Medusae Fossae buried ice. Each of these is a specific candidate, a place where the specific combination of conditions most favorable for life or for the preservation of life's traces is concentrated. This is not the Mars of the cold, dead planet paradigm. This is a Mars with a complex, heterogeneous subsurface that is still in some places, in some ways, hydrologically and possibly geochemically active. A Mars that was habitable in specific locations for much longer than the surface record suggests, a Mars that might still be habitable in the most extreme and restricted sense in the specific environments that the radar is finding. Now, let me address something I've been circling around but haven't said directly. The specific question that the subsurface radar data is ultimately about: is anything alive down there? I want to answer this with the same precision I've been applying to the physics, not with wishful thinking, not with the instinct to find a dramatic conclusion, with the specific quantitative evidence-based reasoning that the data actually supports. The short answer is, we don't know. And the longer answer is, the evidence from the radar is consistent with environments where life could have arisen and might have persisted, but it does not directly detect life. Radar cannot detect life. It detects dielectric properties, electromagnetic responses, and from those, we infer what physical material is present. If liquid brine is present in the South Polar region, radar can detect it. Whether that brine contains living organisms is a separate question that radar cannot answer. What the radar can do, and is doing, is identify the specific locations and depths where liquid water or briny water is most likely to be present. It's creating a map, imprecise, contested at the margins, but real, of where the subsurface water is. And water is the prerequisite. You don't search for life without first knowing where the water is. The radar has found the water, or the most probable location of it. That narrows the search. That makes the next instruments the drill, the penetrometer, the life detection chemistry targeted rather than random. You don't drill everywhere hoping to find something. You drill where the radar tells you the water is. The specific locations MARSIS, SHARAD, and RIMFAX are identifying are the priority targets for the next generation of Mars missions. Not just scientifically interesting locations, the specific locations where the probability of finding liquid water, and therefore the probability of finding life or its traces, is highest based on the best evidence currently available. There's something down there. The radar has told us where to look. In part 3, I want to bring all of this together into the complete picture of what the subsurface radar data means for the future of Mars exploration, for the design of missions that will follow Perseverance, and for the deepest question that all of this is ultimately about. What it would mean for science, for our understanding of our place in the universe, for the question of life's prevalence if the something down there turned out to be alive. So we'd arrived at this place where the radar picture of the Martian subsurface is specific, data-driven, and genuinely surprising. Liquid brine pockets under the south polar ice cap, sustained by a combination of perchlorate, antifreeze, and localized geothermal heat. Anomalous, deep reflectors in the Hellas Basin sedimentary sequence. Subsurface fracture networks in Jezero crater indicating prolonged post-lacustrine fluid activity that directly connects to the biosignature samples Perseverance has already cached. The radar has found the water, or the most probable locations of it, and the next instruments, the ones that will go to those specific locations and determine what's there, will answer the question the radar cannot. Now I want to bring it all the way home to the future missions this data is motivating, to the specific scientific program that connects the radar findings to the life question in the most direct possible way, and to the deepest version of what it would mean for everything we understand about life, about the universe, about ourselves, if the something down there turned out to be something alive. Let me start with the missions, because the radar data is not just scientifically interesting, it's operationally consequential. It's changing what missions get proposed, what instruments get designed, and what questions the next generation of Mars exploration is organized around. The most immediate consequence of the RIMFAX findings in Jezero crater is the scientific prioritization of the Mars Sample Return Mission. We've discussed MSR in multiple conversations, the plan to retrieve Perseverance's cached cores, bring them to Earth, and subject them to the full analytical power of terrestrial laboratories. The RIMFAX data doesn't change the basic plan, but it changes the interpretation framework, the specific hypotheses that the sample analysis will be testing. Before RIMFAX, the scientific case for MSR was primarily about the surface lake. Jezero was an ancient lake. The sedimentary rocks at its floor and delta preserve a record of the lake's chemistry and possibly its biology. Returning those rocks to Earth and analyzing them for biosignatures, organic compounds, isotopic fractionations, morphological features would tell us whether life existed in the lake. After RIMFAX, the case is richer and more complex. The surface rocks are connected to a subsurface fracture system. The fractures carried hydrothermal fluids upward from depth. The carbonate minerals that make the margin unit rocks so astrobiologically interesting precipitated from those fluids, not just from the lake water above. The biosignatures preserved in those rocks might be the traces of subsurface organisms, chemolithotrophs living in the fracture system, not just photosynthetic or heterotrophic organisms living in the lake. This means the sample analysis program needs to test two hypotheses simultaneously. First, did photosynthetic or heterotrophic life inhabit the ancient lake? Second, did chemolithotrophic life inhabit the subsurface fracture system, and did the products of that life get carried upward and trapped in the carbonate minerals? Distinguishing between these two biosignatures, if either is present, requires specific analytical approaches. The carbon isotope fractionation produced by photosynthesis is different from the fractionation produced by chemolithotrophy. The specific organic compounds produced by different metabolic pathways have different molecular structures. The spatial distribution of biosignatures in the rock, whether they're concentrated at specific horizons consistent with lacustrine deposition, or whether they follow the fracture geometry revealed by RIMFAX, tells you about the source. The sample analysis program, when the cores reach Earth, will be extraordinarily detailed. Not just is there a biosignature, but what type of biosignature, from what type of organism, from what specific environment, at what depth in the geological sequence. The RIMFAX data is the geological context that makes these more specific questions answerable. The most ambitious consequence of the South Polar Radar findings is a new mission concept that has been gaining traction in the planetary science community, a dedicated South Polar drilling mission. The concept is straightforward in principle and extraordinarily challenging in practice. Land a spacecraft on the South Polar region of Mars, ideally near one of the Mars's bright reflectors. Deploy a drill capable of penetrating 1.5 to 2 kilometers through the polar ice cap. Reach the hypothetical brine layer, sample it, analyze it for chemistry and for life. The technical challenges are substantial. A drill capable of penetrating 1.5 kilometers of ice and rock in the Martian environment with its temperature extremes, its low atmospheric pressure, its communication delays doesn't currently exist in a form that could be delivered to Mars within a practical mass budget. The deepest drill ever deployed on Mars was the InSight HP cubed mole, which was designed to penetrate 5 meters and failed to reach even that depth due to unexpected soil properties. A 1.5 kilometer drill is 3 orders of magnitude more ambitious. But the concept is being taken seriously. NASA's Jet Propulsion Laboratory and several university research groups are studying the requirements. The Europa Lander concept, a mission that would land on Jupiter's moon and drill through its ice shell to reach the subsurface ocean, has driven substantial investment in deep ice drilling technology that is relevant to the Martian South Polar problem. The specific challenges are different. Europa's ice is colder and the shell is thicker, but the engineering lessons transfer. The timeline for such a mission is not near term. The earliest realistic scenario, assuming funding and technology development proceed, puts a South Polar drilling mission at the late 2030s to 2040s. But the scientific case is compelling enough that the concept is appearing in the long-range planning documents of both NASA and ESA. The MARSIS data, the specific locations and depths of the bright reflectors, is the navigation system for this future drill. Without the radar map, a South Polar drilling mission would be guessing where to go. With the radar map, the drill has specific targets, specific locations where the probability of encountering liquid water is highest. The radar does the reconnaissance. The drill does the sampling. There's a nearer-term mission concept that addresses the Martian subsurface from a different angle, one that could provide crucial context for the South Polar drilling mission, and that is relevant to the full range of subsurface radar anomalies. It's a geophysical network, multiple small seismometers deployed at different locations across the Martian surface, operating simultaneously to characterize the planet's interior in 3 dimensions. The single InSight seismometer provided invaluable data about Mars's internal structure, crust thickness, core size, mantle properties, but its single station limitation prevented the kind of full 3-dimensional imaging that a network of seismometers enables. A 4 to 6 station seismic network with stations distributed across the planet to provide good spatial coverage would enable seismic tomography of Mars's interior. The same technique used in terrestrial earthquake seismology to image the structure of Earth's mantle and core could be applied to Mars, providing a 3-dimensional map of density and seismic velocity variations in the Martian interior. Why does this matter for the radar story? because the key uncertainty in the south polar liquid water hypothesis is the local geothermal heat flux, whether there's enough heat flowing from the interior to maintain liquid brine at 1.5 kilometers depth. A seismic tomography network would directly image the thermal structure of the Martian mantle in the south polar region, identifying any magmatic intrusions or locally elevated heat sources that could provide the extra thermal energy the liquid water hypothesis requires. It would also provide independent constraints on the depth and geometry of the Martian crust mantle boundary information that feeds into the thermal evolution models that predict where in the crust liquid water could currently exist. The InSight seismometer constrained this globally. A seismic network would constrain it regionally with specific resolution in the areas where the radar is finding the most anomalous features. This mission concept, a Mars geophysical network, is in the medium-term planning horizon. It's more achievable than the South Polar drilling mission, but more complex than a single instrument lander. Several concepts have been studied, and it remains a high priority in the planetary science decadal survey recommendations. Now let me address something that I've been deliberately holding back, a finding that bridges the radar story and the broader Mars astrobiology program in a way that I think deserves its own careful treatment. In January 2026, published in a major journal, covered extensively in the planetary science community, an international team led by researchers at Imperial College London reported the most detailed analysis yet of the RIMFAX data from the margin unit of Jezero crater, combined with Perseverance's surface measurements of the rock chemistry. The finding was specific and striking. The subsurface reflectors in the margin unit, the steeply dipping fracture-like features that RIMFAX detected in earlier analyses are spatially correlated with specific surface chemical anomalies. The rocks directly above the fracture reflectors have elevated concentrations of carbonate minerals, elevated signatures of alteration by aqueous fluids, and in several cases, elevated concentrations of organic carbon compounds detected by Perseverance's Sherlock instrument. The correlation is not perfect. Not every fracture reflector has a corresponding surface chemical anomaly, and not every surface chemical anomaly has a corresponding fracture reflector beneath it, but the correlation is statistically significant. It's not random. The places where RIMFAX sees the deepest and most pronounced fracture network are the same places where Sherlock sees the most chemically altered and organically enriched surface rocks. This correlation has a specific physical interpretation. The fluids that moved upward through the fracture network, hydrothermal fluids from depth, deposited their chemical cargo in the rocks at or near the surface. The carbonates precipitated from the rising fluids. The organic compounds, if they're biogenic, were carried upward from depth by the same fluid flow. The fracture network wasn't just a hydrological feature, it was a conduit that connected the deep subsurface environment to the surface rock, chemically linking the two. And the cores that Perseverance has cached the specific samples selected by the science team for their high astrobiological potential are disproportionately from locations that RIMFAX now identifies as being above the deepest and most pronounced fracture reflectors. This is the connection. The samples that will be analyzed on Earth for biosignatures are the samples most likely to contain traces of whatever chemistry, biological or abiotic, was operating in the subsurface fracture system. The radar navigation has been working retrospectively even before the RIMFAX team had fully mapped the fracture geometry. The science team's intuition about which surface rocks were most promising, driven by the chemistry and mineralogy they could measure from the surface, happened to pick rocks that are now revealed to be the ones most connected to the subsurface hydrothermal system. This isn't coincidence. The same hydrothermal fluid flow that created the subsurface fracture geometry also created the surface chemical anomalies that made these rocks look interesting. The surface chemistry and the subsurface structure are two expressions of the same physical process. Finding one led to the other. Now let me bring this to the deepest version of the question. What would it mean if there's life down there? Not in the specific technical sense of what it would mean for the Mars sample analysis program or for the design of future missions. In the broader sense, in the sense that matters for how we understand our place in the universe. We've established across multiple conversations in this series that the argument for life being common in the universe is compelling. The chemistry is universal. The building blocks are delivered everywhere. Life arises quickly where conditions are met. Extremophiles colonize every accessible niche. The argument converges on the conclusion that microbial life is probably widespread in the galaxy, but that argument rests critically on one point: whether life arose independently more than once. On Earth, we have one data point, one origin of life, one lineage, descended from a single common ancestor. We don't know if life is easy, something that arises readily wherever conditions are met, or hard, something that requires extraordinary specificity of conditions and time that was, on Earth, achieved by extraordinary luck. If life existed on Mars independently, then we have two data points, two origins of life in the same solar system. And two independent origins of life in the same solar system, in a system where the planets are chemically similar, where the same cometary chemistry was delivered to all the inner planets, where the conditions for life were met on at least two planets, would be extraordinarily strong evidence that life arises readily wherever conditions are met, not two planets. The same solar system, a system of 8 planets and dozens of moons, in which two rocky worlds developed independent living chemistry, that's not a coincidence. That's a signal that the origin of life is not a miraculously unlikely event, but a physically expected outcome of chemistry in the right environment. Two origins of life in the solar system would, in my assessment, be the single most important scientific discovery in the history of our species. Not because of what it says about Mars specifically, because of what it says about the universe, about the prevalence of life throughout the galaxy, about whether we are alone, the something buried under Mars, whatever the radar is detecting is connected through this chain of reasoning to the deepest question about our place in the cosmos. Let me now say something that I think is important and that doesn't get said enough in discussions of the Mars subsurface findings. The radar data is real. The anomalies are real. The debate about their interpretation is real and ongoing, but the uncertainty is also real. We don't know what the South Polar bright reflectors are. We don't know whether the Hellas Basin deep reflectors represent ancient brine or unusual volcanic mineralogy. We don't know whether the Jezero fracture system was inhabited. I presented these findings with the enthusiasm they deserve because they're genuinely important and genuinely surprising. But intellectual honesty requires acknowledging that consistent with liquid water is not the same as confirmed to be liquid water. Associated with organic carbon is not the same as produced by biology. Evidence of subsurface fluid activity is not the same as evidence of life. Science works by ruling out alternative explanations, not by embracing the most exciting one. The history of Mars science has several cautionary tales. The ALH 84001 meteorite controversy, where features in a Martian meteorite were initially interpreted as possible fossil biosignatures, and subsequent analysis showed they could be explained by abiotic chemistry. The early interpretations of the methane measurements by Curiosity that suggested biological methane production and were subsequently shown to be more consistent with geochemical rather than biological sources. The Mars subsurface radar findings might follow the same trajectory: initial excitement, more detailed analysis, mundane explanation, or they might not. They might, as analysis continues and new data comes in, become more compelling rather than less. What we can say with confidence is that the radar data is telling us something genuine about the Martian subsurface. The planet is more complex underground than the surface records suggested. There are environments there, specific, localized, defined by the radar geometry, that deserve detailed investigation. The priority targets for the life question have been identified not by speculation, but by physics. By the specific electromagnetic properties of specific materials at specific depths. The radar has given us a map. The map says, here, look here. Let me close with something that I think is the most important conceptual point about the entire Mars subsurface radar story. For most of the history of Mars exploration, the entire history, from the early telescopic observations through the Viking landers, through the Mir rovers, Mars was studied through its surface. What we knew about Mars was what the surface told us: the surface rocks, the surface chemistry, the surface morphology, the ancient river channels visible from orbit, the delta deposits in Jezero crater, the layered sediments of the polar caps. The surface is an extraordinary record, but it's a record of the past. The processes that shape the surface, the ancient lakes, the river systems, the volcanic eruptions, are largely gone. What remains are their traces, their deposits, their geological signatures. The subsurface is different. The subsurface is where the present is happening, where water, if it still exists on Mars, exists now, where any biology, if it still exists on Mars, exists now, where the geochemical processes that might sustain life, the water-rock reactions, the hydrothermal systems, the slow chemistry of deep aquifers, are operating in real time rather than as ancient history. The radar instruments MARSIS, SHARAD, RIMFAX are the first tools we have that genuinely reach into the Martian present, not the ancient past preserved in surface rock. The current state of the planet's interior, the distribution of water right now, the structure of the subsurface right now. And what they're finding, the bright reflectors, the anomalous geometries, the fracture networks, is not the story of a dead planet's ancient history. It's the story of a planet that might not be entirely dead. A planet whose interior is more active than the surface suggests. A planet that might still have liquid water in specific, localized, extreme environments, doing what liquid water does wherever it exists in the presence of chemical, energy, and mineral surfaces. Chemistry, reactions, possibly, just possibly, something more. There's something down there. The radar has told us this with specificity and with physics, not vaguely specifically. At 1.5 kilometers depth under the South Pole, in a region covering tens of square kilometers, there is a material with a dielectric permittivity too high for dry rock or dry ice, too high for the known minerals of the Martian South Polar region, consistent with liquid brine maintained at the edge of what chemistry allows. At depths of 100 to 800 meters in the eastern Hellas escarpment, there are reflectors whose geometry and properties suggest ancient lake sediments with possible aqueous infiltration. In Jezero crater, at depths of meters to tens of meters below the surface that Perseverance is driving across, there is a fracture network that once carried hydrothermal fluids from the deep subsurface to the near surface, depositing chemistry in the rocks that the rover has been sampling. These are not anomalies in the sense of being suspicious or controversial in a way that undermines their reality. They're anomalies in the scientific sense, observations that don't fit the simplest model, that require explanation, that point towards something more complex and more interesting than the standard picture. The physics demands an explanation. The dielectric permittivity requires a specific material. The fracture geometry requires a specific process. The correlation between the radar structure and the surface chemistry requires a specific mechanism. And in each case, the explanation that best fits all the data, not the most exotic, not the most exciting, the one that best fits all the data, involves liquid water. Either current liquid water in the polar brines, or ancient liquid water in the Hellas sediments and the Jezero fractures that left its physical and chemical signature in the rock. Water is not life, but water is where we look for life. And the radar has found water, or the strongest evidence we currently have for where water is in the Martian subsurface. The next chapter of Mars exploration will be organized around what the radar has found. The drill will go to the South Pole because Mars has told us to look there. The sample analysis will focus on the fracture zone cores because RIMFAX told us those were the connections to the deep subsurface. The seismic network will image the thermal structure in the South Polar region because the bright reflectors demand an explanation for their local heat source. The radar did reconnaissance. The drill, the seismometer, and the laboratory will follow. And when they do, when the first brine sample is drawn from 1.5 kilometers below the Martian South Pole, when the Jezero fracture zone cores are analyzed by mass spectrometers in clean rooms on Earth, when the seismic tomography reveals whether there's a magmatic intrusion providing the geothermal heat that the brines require, we will know more than we have ever known about whether Mars is or was alive. Not because we were lucky, because the radar told us where to look. There's something down there. And we are right now, with these instruments, in this generation, finding out what it is. The physics says it's water. Maybe ancient, maybe current, maybe barely liquid, at the edge of what chemistry allows. And if it's water, the next question writes itself. Is anything swimming in it? We don't know yet. But we know where to look. And that after decades of searching, is everything